Hello friends, today we're going to look at hypothesis testing. The objectives of this chapter will mainly be to really understand the logic behind hypothesis testing, what concepts are imbued in the null hypothesis and the alternative hypothesis, what is the alpha and the test statistic. We will need to also understand what it means to reject the null hypothesis, what it means to fail to reject the null hypothesis. We'll also look at specific examples for a one sample where hypothesis testing will be appropriate, how exam questions come in that context, and perhaps we'll also test the significance of a single sample with means and proportions using the 5-step model. We'll also briefly explain the difference between a one-tailed test and the double-tailed test. And finally, we'll explain the differences between type 1 and type 2 errors. The next session, that's where we'll discuss the t-distribution and how it is used. So hypothesis testing essentially is mainly designed to detect the differences between two means. If the differences that occurred have a significant difference, in an applied perspective, you are dealing with an organization that claims to be selling a bag weighing 50 kgs, but on the actual ground, you discover that they're actually selling 45 kgs and stealing 5 kgs from the market. The differences, are they significant enough for us to say these are stealing from people and these are not stealing from people? So hypothesis testing in that regard is also called significance testing. You want to ideally test the differences if they're significant or not. So in this chapter, we'll focus on one sample where we're going to compare a random sample against a population. We're also going to compare a sample statistic to a hypothesized parameter to see whether they're statistically different. So a statistic sample is one which you actually measure. A hypothesized one is one which is hypothetic. And this takes us to our question to say, what is hypothesis testing? Hypothesis testing is basically testing a claim or a belief. This is what is called a hypothesis. So the steps that are included in hypothesis testing are: number one, you need to state the hypothesis. What assumption do we want to measure? The second step is to state your level of significance. The third step will be to actually calculate the Z statistic. Then we'll make our decision and conclusion thereof. So these steps, once understood, it'll be easy to follow through properly. So just to make it applicable, are people who have been treated for alcoholism more reliable workers than those in the community? We want to test this and want to see whether there's an effectiveness in reliability between those who are treated and those who are not. So this is a clear example of how hypothesis testing could be. You're testing samples of reliability between two groups. So we have been given a sample from the community which is giving 7.2, and here a sample of those that were treated in terms of reliability is giving us 6.8. Clearly, the difference that you are seeing here, is it significant enough or not? So that is what hypothesis testing is going to be all about. And for this class, we're going to use the Z test, which deals with samples that are more than 30 to analyze the questions for this study. So whenever we're dealing with hypothesis testing, we're actually asking ourselves a question to say, are the samples the same or they're different? If they're the same, it means we are accepting our hypothesis, our HO, our now hypothesis. If they're different, it means we're rejecting our now hypothesis. So whenever we are accepting our now hypothesis, of course, at this level, we're using the word fail to reject as much as possible. We should be avoiding the word accept. So with the steps that I've talked about, I'll also give you a run through of the formulas we're going to use. We're going to use formula for the Z, which is x bar minus mu, standard deviation over root n, where n is greater than 30. We're also using a proportion formula where we have p hat minus p over pq over n square root. Now, just going through our steps again. The first step is we need to set up the null hypothesis, which is a statement that suggests that the value of the parameter that we are trying to test is either true. So our null hypothesis is simply the claim that we are looking at. We are either going to reject or accept it. So we abbreviate our null hypothesis as HO or H0, which is denoted by mu. An alternative hypothesis, which is H1, other books will write H2 or HA. So HA is accepted if the test enables us to reject our HO. So whenever we reject HO, meaning we're accepting our HA. So here our alternative hypothesis could either be mu is equal to the same figure that you have on top there. This means that it's two-tailed test. Or mu is less than the figure that is in the null hypothesis. It means that is a one-tailed test. So the one-tailed test has only two signs, greater or less than, meaning you're looking at it from one particular angle. If you're dealing with a two-tailed test, what we're going to have here is equal to or not equal to. So in this regard, our second step will be to state the level of significance. Now, the level of significance simply expresses your probability of rejecting the null hypothesis when it is in fact true. We usually work with a 5%, which is the standard. We usually work with a 5%, which is our standard. If you're not given, we use 5%, but we also have other levels of significance like 1%, 2%, 5%, and 10%. The difference from 100 is what we call the confidence level. Then we have our rejection rule, which is based on the significance levels that are given. So we always reject if our answer falls within the shaded regions of the critical values that we're going to discuss. Then our fourth step is to test a statistic, to calculate the test statistic. This Z formula is actually what we call a test statistic. In abbreviation, it is denoted by mu, alpha n over alpha over root n. So this is just the same as the formula that I was just showing you a while ago. So whenever the answer we get is greater than the tabulated figure, in that case, we would simply conclude that we are rejecting. Otherwise, we fail to reject. And the last step is mainly that of making a conclusion and a decision. We make a conclusion and decision based on the answers that we would have gotten. So I'll start with basic examples that will allow you to understand how hypothesis testing is computed. Then we'll go to applied questions from an exam perspective so that we'll be able to really refer. So we have to test the following hypothesis. Our HO mu is equal to 50, our H1 mu is not equal to 50. Already this gives us a picture that this is a two-tailed test. because the sample that we're dealing with in this case has the signs that are showing above. Now, if I could briefly deviate, the purpose of this section of our session, we're going to concentrate on 4 confidence levels. So we have 99%, we have 98%, we have 95%, and we have 90%. Of these confidence levels, our standard is 95%. We're not given. This is the one we actually consider the most. So our Z values for a two-tailed test. I'll not show you how these values were calculated, but I just need you to remember them for the sake of this session. So at 99%, we have what we call 2.58. This is for a two-tailed test whose signs are greater, equal to, or not equal to. These are the only 2 signs that will give us an idea that this is a two-tailed test. Then here we have 2.33 for 98%. And here we have 1.96. And here we have 1.64. So this is our Z value. Here we have 2.33. We have 2.05. We have 1.645. And we have 1.28. Now these are the critical values that you need to know, or preferably you need to master. The difference from 100 is called our significance level. So here we have 1%. Here we have 2%. Here we have 5%. And here we have 10%. That is the difference from 100. The 2 must add up to 100. Then our alpha here is 0.10. Just dividing the significance level by 100. Here we have 0.05. And here we have 0.02. Now these are very cardinal for you to making a decision as to whether to accept or to reject. So if you're given, for instance, a level of significance at 99%, and it's a two-tailed test. So this is how the shading will look like. Regardless of the answer you're going to get, at 98% confidence level, we're going to accept our answers that will fall within this unshaded region. We're going to reject our answers that will fall in these rejection regions. So I want us to practice briefly from what I will draw here. I'll draw 3 key bell-shaped diagrams because normal distribution goes hand in hand with our hypothesis testing. So I'll tell you 3 things about these 3 figures here, A, B, and C. And I'll ask you just a short while after I'm done. So figure A is a two-tailed test. If this is a two-tailed test and this is at 99%, so it means our lower critical value here will be 2.58 and our positive critical value will be 2.58. The same value will be here. If this is 95%, here we have 1.96, which is this figure here, and here we have 1.96. For figure B, this is a single-tailed test, and the signs for single-tailed test are greater or less than. So this one is clearly less than. So the sign that should appear in the alternative hypothesis is symbol less than, because we are shading on the left side. However, if we're at 95%, the critical value here is 1.645 instead of 1.96. And figure C is our single-tailed test whose Z value will be a positive. So in this case, for you to know whether this is a negative and a positive Z figure you're going to get, this will usually give you a sign whenever your mean, your X bar, is less than your mu. Just know that you're going to get a negative. Whenever your X bar is greater than your mu, this is what will typify the bell-shaped. In short, if your mean is less than the mu hypothetical, you're going to get a negative Z, and you're going to use a single-tailed test. I need you to have these at your fingertips. So I'm going to give you a hypothetical example just on this to summarize everything I have explained. So we are given our mu in the null hypothesis as 10. We're given our mu in our alternative hypothesis by the same figure 10. Then our alpha will be 0.02. Our n, our X bar will be 15. Our standard deviation will be 16. And our n will be 64. I'm going to analyze each of these parameters that have been given. To start with, 64 is a sample size greater than 30. It gives us authority to consider having to use a Z. Our standard deviation is 16. So the two formulas that I discussed, we're going to use the standard deviation Z formula. We can't use the proportion because we don't have a proportion. Similarly with this X bar. Now, these both are means, except that this mean is called mu, hypothetical mean. It has no sample size attached to it. This one is our X bar. It has a sample size attached to it. The sample size that produced at 15 is 64. So using our 5-step formula, state the hypothesis. I will not write the hypothesis again. It's already step 1 here. Step 2, state the level of significance. Our level of significance is what? 2%. From our alpha 0.02, just multiply times 100 to get a percentage. Step 3, state the decision rule. So our tails here are double because of the signs that we have there. So I'm going to shade here. I'm going to shade here. So here we're going to have 2.33. From the table, 2.33 has been given to stand for what? Our Z. So when you go here, you check under 0.02 for a two-tailed test. This is 2.33. So We are now going to understand that the answer we're going to get, if it falls within here, we will do what? Fail to reject. Of course, this is accept. As much as possible, we at postgraduate should avoid the word accept. We'll say fail to reject. Now, our decision rule is simply either stated by this, or you can accompany the word to say we do what? We reject. We reject HO. Pardon my handwriting, I'm using a cursor. Reject HO if Z calculated is greater than 2.33 or Z calculated is less than negative 2.33. These are called our critical values. Now we go to our fourth step where we calculate what is called the test statistic. Our formula for the test statistic will be x minus mu over standard deviation root of n. So here we're going to look at our x bar. Our x bar in this case is the 15. And our mu is a 10. Our standard deviation is a 16. And our root of n is 64. So the difference in the mean is what we're actually interested in. If this was an exam question, it could say government claims that only 10 people contract COVID in every large gathering. At 0.02 alpha, 64 gatherings were tested and found that the mean infections of COVID were 15, standard deviation 16. Test the claim. There's a significant difference. So we are testing what the doctors are telling us and what we actually found in the ground. So there was a difference of 5. Now this difference of 5, was it significant enough for us to probe them to say, you guys, your assumptions are false? So you divide 5 divided by 2. This is a standard error. The square root of 64 is 8. 8 into 16 is 2. And 2 into 5 is 2.5. Then we're going to locate the 5 in this bell shape. 2.5 is somewhere here, which is in the shaded region. So we're going to now reject HO at 2% level of significance, since our Z calculated is greater than 2.33. Therefore, there is a statistical difference between the two means. Notice in my conclusion, I've mentioned 5 key things. Number 1, I've mentioned my level of significance. Number 2, I've mentioned my decision. So we reject. You don't end here. You substantiate why are we rejecting and at what level are we rejecting. We reject HO, that is number 1. At what? At 5%, or this is 2%, at 2% level of significance. Very important statement. Why? Since Z calculated you can put it in brackets, 2.5 is greater than 2.33. So what? What does that mean? It means there is a significant difference. So whatever we get is inside here, there is no significant difference. and this there is no. In here, that there is a significance what? Difference. So it is important to be holistic in your conclusion. At HO, we reject our HO. By rejecting HO, it means we're embracing our HA at 5% level of significance. Since our Z calculated is greater than 2.33, therefore, there is a statistical difference. Remember, hypothesis testing is also called what? Significance testing. So now, let me take you to a word problem so that we can understand more how this is applied. So I will, without writing, take you through this question. A farmer who has used a specific fertilizer for many years knows that his average yield is 2.5 tons per hectare, with standard deviation 0.53 per hectare. The fertilizer is discontinued and he has to use a new brand. He suspects the new fertilizer might alter the yield, but he has no idea whether it will be an increase or a decrease. At the end of the season, he finds that the average in 35 plots has been 2.65 tons per hectare. At 5% level of significance, test whether this sample is statistically different. Now, this question is pregnant with a lot of information that is vital. Number one, we've been given a historical mean 2.5. So this is called our mu. It is what? A historical. Secondly, we are going to analyze the formula to use for a given standard deviation and we're given our sample size. So our mu is 2.5, our standard deviation is 0.53. Now we're told that this guy does not know whether it will be an increase or a decrease. So since he does not know in advance which direction to use, we are going to now assume that this is a two-tailed test. But if he knew that it will be an increase, we're going to use greater than here. So meaning this will be a single-tailed test. And at 5%, we have 1.645. But this is a double-tailed test. So if you remember from what we're discussing, you need to have this table at your fingertips. So we are going to have this table at our fingertips. So at 5%, two-tailed is 1.96, single-tailed is 1.645. So this is how it's supposed to be done. So we'll continue further on. At level of significance 5%, since that's been given, we're now going to use our decision rule. 5% here is 1.96 and here is 1.96. The 1.96 will be negative this side and positive this side. It's coming from a critical value of 5% here. So we are going to reject our now hypothesis. Our Z calculated is greater than 1.96. Whenever I put this critical value here, it means on both sides, whether it's negative or positive, we're rejecting. So this diagram simply illustrates our decision criteria. Then we calculate our Z, which is given by this formula, x bar minus mu, standard deviation over root n. So 2.65, according to this question, has been given as our x bar because it was calculated from 35 plots. So n is 35, and n is giving us power to use our z instead of a t. And 2.65 is our x bar. Now let me throw it to you. If it is assumed that a baby weighs 5 kgs, then we weighed 100 babies. It was found that they weigh 3 kgs. Which one is statistical and which one is hypothetical. And we use a Z and we use a T. Somebody? So we use a Z because this is a sample more than 30. If the sample is less than 30, we use a T. This 2.65 is our X bar because it was calculated from 35 plots. So when we calculate this, we get 1.67. So this, we now identify it, whether it's inside or outside. Now 1.67 is somewhere here, inside. And so at this point, we are going to what? Accept, or rather say we cannot reject HO since it's within, it's less than 1.96. And what is our conclusion? There is no statistical difference. So in an applied perspective, we're dealing with a farmer who wants to compare the new yield to the old yield and to find out whether or not we need to continue the new yield. So whenever we reject HO, there's a significant difference on board. Whenever we fail to reject, it means there's no significant difference. So in this regard, we will safely say we are going to fail to reject.
Some of your kids try using their nails is a good way to teach them.
So we now go to our single-tailed test, where we're going to look at a company that has semi-skilled workers in an industry, and their mean salary is 286 and standard deviation is 29. Now this company has 40 workers, and these workers want to go on strike. Their average is 271 salary, and they want to accuse this company of paying inferior wages. So to start with, the word inferior gives you a synonym of less than. So this gives us an idea that this is a single-tailed test. And usually when you're not given our level of significance, we assume it is 5%. And at 5%, our level of significance is 1.645. So what do we put in our null hypothesis? We put 2.58, 2.86.5. The null hypothesis has no sample size attached to it. The alternative hypothesis has a sample size attached to it. So the 40 workers are the ones that produce 271. So this is what we're going to put on our X bar. Now, just to give you an idea, whenever our X bar is less than our mu, we're usually looking at the left tail. It is a single-tailed test because we are shading on the single side. So we are, in this case, going to say we are going to reject if our Z calculated will be less than 1.645 this direction. So we're using a negative because we're dealing with the negative quadrant. So when we calculate the Z here, we're going to get negative 3.16, which is in the shaded region. So whenever our answer is falling in the shaded region, we're obviously concluding that we reject our HO. So by rejecting, it means there's a statistical difference. So we want to evaluate whether the workers in this company are being paid inferior wages. So we reject HO to say that no, they're okay. We are accepting HA to say they are being paid inferior wages. So by rejecting It means that we are accepting the fact that this company pays inferior wages. So this is how we do a single test for one sample. In our next session, we're going to look at how to deal with two samples, also how to use the p-value. So we're going to end here for now. Unless there are any questions you could ask now.
Good afternoon, Mr. Collins.
Good afternoon.
Could you please just explain the last part you were saying? If the X bar given is less than our mu, then you expect it to be a left-tailed curve?
So just a logical explanation. When this X bar is less than the mu, the answer we're obviously going to get is a negative here. That's the rationale behind that. So we're going to get a negative in the fact that this